Hello, I thought I'd record a short follow-up to the 3D printed Axleboxes video, which I hope you may have seen on the site. That project, on the face of it, appears to be a failure and something that didn't work. At least it didn't work as well as I'd hoped. But I think there were some lessons to be learned and to be passed on here, which are probably quite important. So I thought I would try and summarise some of the things certainly I've learned through doing this, and some of my reasons for tackling the project in the first place. To start off with, should we have expected the failure? Why did it fail? And what we learned from the failure? So what was the failure expected? Well, to an extent, this is not an application that I envisaged when I purchased the printer. My thought with purchasing an FDN printer, having read about the various printing technologies, what they can do and their limitations, is I'll be using this printer for predominantly non-scenic type projects. So things like brackets to hold things, maybe the structure which would have some material over the top, boxes, that sort of thing, rather than final finished models where we would be seeing the finish that's been printed by the printer. To an extent, this is what FDN printers have been used for a long time for, and home printers, certainly people do make models out of them, and you can, with some work, make them look good, but they're not traditionally used for very fine detailed items. So why did I start this project? Well, in part, I was quite impressed with the early items that I produced with the printer. The detail was much greater than I'd expected, so I thought I'd give it a go. I also needed the particular item in question, so I thought, what have I got to lose by trying it with the printer? And if nothing else, I could learn a lot about the limitations of the printer, whether it could do this or not. So why did it fail? Well, one thing we saw with the prints, that if you looked at that video you would have seen, was the stringing effect on the print itself. So when it came out, it looked something like this on the print bed, which wasn't very nice. Shouldn't have looked like that. I've not seen it much before. The other thing was that some of the areas were very thin. So looking at the model that it's based from, the area that I've circled in red, is actually only 0.2 of a millimeter thick, and this is perhaps too thin to be printed by my printer. But we'll go into more detail on both of these in a second, and how to fix them. And indeed, as we say here, where that area is circled there, nothing was actually printed by the printer. So to start off with, the stringing effect. Why did I get this? I'd printed lots of things before, and occasionally seen a little bit of stringing, but nothing to the extent that I'd seen here. And what I discovered is this is an environmental effect. It's actually caused by cold and draft, setting the resin too quickly as the nozzle is being pulled away from the model. The way the printer works is, in order to come to the end of printing a line, it retracts the resin slightly back into the nozzle to, if you like, break away from the amount that's been laid down on the surface. And in cold or draft, where it's cooling too rapidly, what that means is as it pulls away, it starts to set and it forms a string, and rather than breaking away cleanly, you get this stringing effect. So I did reprint the same thing without any other changes at all in a warmer, draft-free environment. And this is the effect I got, which, as you can see, is quite a lot better than the first one. Now, to be fair, that first one was printed during the cold spell we had in early February in an unheated room, which had drafty windows, so that probably explains it. Even the second one is not as good as I have seen in the past, and is probably down to the fact there were still drafts and it was somewhat colder than usual. But you can very clearly see in this one the area that's not been printed, as we will look at now. So the non-printing area. Is it simply too fine? Is that why it didn't print? If we zoom in on that, you can see exactly what's happened. There appears to be no filament there at all. All we see is a few strings that have been laid down as it's gone from the leaf across to the hanger part of the spring. Is it printer resolution that's caused this? And indeed, what is the printer resolution? We've got a number of factors here. There's the layer height, there's the width of the nozzle through which the filament is being extruded, and there's something called shell thickness, and we're going to examine all of those in a second. So layer height. What is layer height? It's effectively how much the printer moves up every time it does a layer. And this is settable in the sighting application. You can actually say how much you want it to go up, and it will change. So you can use this as a way of trading off the speed of the print versus the quality of the print. If you have more very thin layers, it will take a lot longer to print something, but you will end up with something which has a smoother finish because you have less of a layer size, and the edge of the layer will be smoother than if you go for a thicker layer where you'll get more of a curved shape to the edge of the layer, which will be harder to remove in finishing later. You can remove it. You can use wet and dry sandpaper to sand these things down. Be careful. Don't do it too vigorously. Don't file too vigorously, because if you get this stuff too hot, it will remelt, and you probably don't want that. And certainly if you're using your best file, it will clog your file up. So think carefully about how you finish it. Wet and dry emery paper is probably the best to use. The nozzle size. Well, what is the nozzle size? It's the size of the hole that the filament is deposited through. If you think of a tube of bathroom sealant, which is probably something most people have used at some point in their life to seal things, you have a piston which is extruding the silicone out through the nozzle. The bigger the hole you make in that nozzle, the wider the bead of silicone you get. And it's exactly the same with the filament in a 3D printer. So the width of the nozzle governs in part the X resolution. That is, how much detail you can get in the X direction. If you're trying to make changes that are less than the width of a nozzle, then you're not really going to see them, because the printer is not capable of printing something that's that thin. The default nozzle on my printer is 0.48 millimeters. You can get smaller ones. There are also mechanical restrictions to the X resolution, because you've got the movement aspect of the bed moving from side to side. And so let's look at mechanical restrictions a little bit. Say the print head is fixed in one direction, let's call it the X direction, so it can't move backwards and forwards on the print. The bed moves backwards and forwards, but not the nozzle. That means the whole model moves, and that can have some interesting effects in itself, particularly if the model is not stuck well to the build plate. You'll find flexing going on. You'll find that it will go wrong in interesting ways, and there's an example of that later on in this presentation. The print head moves from side to side, and that gives you the length of runs. The length of an extrusion depends on the ability to stop the filament coming out, which is the thing we said about stringing earlier. So it actually puts down a length of filament, pulls the filament back, and then takes the print head away to come to an end. And now that process obviously is a mechanical process and does have its limitations on resolution as well. Print shell is important. What is a print shell? Well, if you look at a cross-section through something that's 3D printed, you find that solid objects are not solid. You get this sort of effect, where you get an outer shell, which is a number of layers of filament wide, and then inside you have an infill. And there are different infill patterns or different infill percentages you can choose. This is partly done to save on material, but also to save on time. If you were to actually fill a solid object with filament, it would A, cost a lot, and B, take a very long time to print. So we compromise and we create these shells with infills. And the number of layers that make up the shell is configurable. And that's important. And why is it important? Because if there's no shell there, it won't print a solid object, so it will print nothing. And in fact, this is what happened with our springs. It was too small for a shell to be produced, so it didn't print. We should have seen some clues when we looked at the slicer. So what I'm going to do is load the STL file for our spring into the slicing program, and here I've zoomed into a small part to take this screen dump. Then going to slice the model using the default settings. And what you see is this. Now if we look at this, it's very obvious. There are areas that are not printed. The leaf spring doesn't have the top leaf on it that connects it to the two hangers on either side. And this is indeed what got printed. What we saw extra to this, of course, were the stringing effects and supports, that sort of thing, which created more noise. But if we could have seen a clean version of what was printed, this is the best we could have hoped for. So we should have spotted, or I should have spotted at that point, that because there was no shell on that top leaf of the spring, it wasn't going to print. We weren't going to end up with a solid object. The air is just not thick enough to create a shell using a 0.48mm nozzle and the number of layers required for a minimal shell. Another thing to look at then is orientation and resolution. What are the effects of how you orientate something? We've already seen that they're not equal X, Y, and Z resolutions because different factors govern what can be done with them. And in fact, the one you have most control over is the Z resolution, i.e. the up and down. So if we rotate an object on the build plate and slice it again, do we get a different result? So what I've done is I've taken our Axlebox, and I've turned it through 90 degrees so it now rests this way on the build plate, and sliced it. And we do indeed get a different effect. The shell is now determined by the width of the spring and not the height of the spring. So the height is still 0.2mm, but because we've got an ultrafine setting with 0.005 set as the Z-axis step, we can print that part of the spring. So looking at this model, we can certainly print our Axlebox. The eagle-eyed among you will have noticed, however, although the leaf spring is now included, the bearing recess has now become a hole all the way through, and that's because the outer shell wasn't thick enough. It's not able to create a shell there because there aren't enough layers of material with the default settings to create that shell. If you look at the underside of the spring, you can also see that there's no shell on that either. You can see the layers of infill. That's not so big a problem with what we're doing, and in fact wouldn't show in the final print. The other thing we can look at is what the print parameters are that control all of this, and you can change these print parameters. So what I've done is taken my default settings and changed them. So I've said I want a layer height of 0.005. It's a simple one. I've said that the vertical shells, I want the minimum number of extrusions to be one layer. So with a 0.25 nozzle, which is what I've told you I've got, even though physically I haven't got that, that means you can still have a shell with a 0.25 layer of material. I've done other things about the minimum shell thicknesses, for instance, and I've also told it to detect thin walls and bridging in an effort to try and tidy it up. So this impacts the slicing algorithm, and the commands are sent to the printer. The physical printer remains the same, however. I haven't changed the nozzle, although it is possible to change for a nozzle of that size. I don't have one. But I thought I would try. I sliced it with these parameters, and this is what I got. As you can see, we now do have all our leaf springs there. We do have the end of our recess for the bearings in place, so that's back, and we do now have a bottom on our Axlebox. So this is actually looking quite promising. I'm going to try printing it. Of course, there is one problem, which is this is based on having a nozzle that isn't actually in the printer, so I'm not expecting this to actually work. And indeed, with a 0.48mm nozzle, First I printed it with supports, and this is what I got. It's quite hard to tell looking at this picture, unfortunately, because of all the noise and the glare. It's still on the print bed, but you can see that the spring is there, and most of the material is there. If I actually take it off the print bed and give us a closer look, you can see there's a lot of support material and quite a lot of stringing again, probably caused by the fact we have a much thicker nozzle now than it believes we've got. So that's causing it to lay down more material, which is giving us slightly untidy edges to it as well. The other problem with it is that I only put supports from the print bed, so the heavy axle box at the top has sagged slightly. That probably needs more supports in order for this to work. I didn't go any further with this, partly because I don't think adding extra supports would have done much good because of the lack of the correct size nozzle. And I think it's going to be quite hard to remove the supports from this because the item itself is quite flimsy because of the 0.2mm leaf spring. So I then tried it without supports, so no supports on the build plate or any supports anywhere, and this went terribly wrong. I'm not surprised because the contact points onto the print bed were very small, and in fact what happened is everything started to sag under the weight, so you didn't get the defined points at the two ends, but eventually there wasn't enough contact with the print bed for it to adhere, and it actually came loose. So if you notice halfway up the axle box it's turned into a horrible mess. That's because the model became detached from the print bed and was just stuck on the head, which was extruding more and more material but not managing to actually move around in the X and Y direction relative to the print, because the print was just floating in midair. So it is a failure, but it's worth looking at to know what happens if you don't get proper print bed adhesion. So what conclusions can we come to? There are minimums to be considered. The orientation does matter. You can change dramatically what gets printed and how it looks by rotating an object on the print bed. You've got to consider the Z resolution is much greater than the X and Y. You also have to consider that things that are printed face down on the bed will have a smoother finish, because it's the smoothness of the print bed that determines that, as opposed to the layers that you're laying down with the extruder. Home FDM printers are not the right printers for small objects. Well, yes, to an extent that's true. If you're looking for a small object with fine detail, I wouldn't recommend it. If you're looking for something bigger with detail that's within the resolution of your printer, then they're fine. Above all, be realistic with your expectations. This project was really trying to get too much out of this printer. Don't get me wrong, it's a good printer and a very good tool. This is just not the right use of that tool to produce these small, highly detailed, very fine parts. However, I think it was a lesson worth learning, and it is good to explore the limitations of your tools. I hope you found this at least of some interest to you. Thank you.